Hey guys, we're going to take a look at kind of a general review of the module 3314, control circuit and motor troubleshooting. And my plan is to break up the module into smaller sections and smaller videos to make it a little bit easier for you to digest. So we'll get things kind of rolling a little bit and go from here. So we'll go through the classroom PowerPoint and get that rolling. All right, so the first section here that we've done some preliminary lab activities on some of these things, such as taking a look at some of the common devices and looking at relays and contactors and motor starters in the last couple of classes. We're also going to take a look at some of the operation and some of the other devices and controls that are in this particular module. The performance tasks that you guys would have done would have been testing some of the relays and contactors in applications. So let's take a look at the first part. So the first part of the control module on considering common control circuit characteristics is one or more of them are going to control some sort of pressure or temperature or some sort of a humidity device or something that they're going to relate to that. You're going to have mechanisms that are going to take that information and then do something with it. So that might be to turn the furnace on, or it might be to enable a compressor stage, or we're going to allow an economizer to operate, something in that order. It could be, hey, I need to stop a fan from operating or a compressor from operating because of a safety. So those are all things that typically would indeed happen in here. Additionally, you can have different types of wiring and piping and linkages that are connected, or let's call it interconnected to some extent to those particular devices, and that's typically what would indeed happen. A lot of these devices will also use, let's call it a significant amount of energy to do some work and to operate a compressor or a fan, a damper, a valve, anything. It could be something to control gas flow or anything like that, and we have to have some understanding of those. Additionally, obviously, some of those controls I had mentioned earlier, I said they can terminate operations. So what that means primarily is when they're terminating operations, that can also mean that they might sense a safety problem and say, hey, we're going to stop this from operating. So that's kind of what they mean by that. So there might be a problem with a motor safety and they have to stop it. So that's kind of the typical of typical characteristics. So additionally we have, when we started looking at relays, the first class, we had talked about the basic structure of relays, and one of the big things that I've always seen over the years has been an understanding of what do they mean by normally open and what do they mean by normally closed. And with relays, if your only knowledge is that of relays and contactors, it's fairly basic, fairly self-explanatory. It's almost like what is the fail-safe position or the normal position of those contacts, so when that relay would be not energized. And so, obviously, if they have a relay that is set up and they identify this as a normally open contact, you would expect it to have an open set of contacts. So as you can see, there is a gap in between the contacts, which you would not expect to allow any flow of any electrons to do any work at all. They also have a normally closed set of contacts, and of course that normally closed set of contacts is designed to allow flow when that relay is not energized. Now, that is, again, those are normal basic structures. We have relays that might have multiples of those. They might have 2 or 3 sets of poles that would identify that. So, and then obviously the expectation is that when you energize that relay, you would very much expect, when you energize the coil of the relay, you very much expect that action to switch both of those to the opposite of their normal position, is typical what you would expect. And if those don't happen, you'd expect something wrong. So let's take a look at the next thing. So in other words, we talk about, in this particular module, this one here identifies what we would identify as a single pole, single throw relay structure on this particular module. And in this particular relay, we're going to identify one of these legs, or one of those legs are going to be identified as the incoming power that may be, they might be sharing, could potentially be sharing power to a relay coil. It would be, or even a set of contacts, whatever it might be. So there's a couple of options where that might be. Now, in some situations, what I'm going to show you is this. Schematically, this is probably somewhat important. Schematically, you might see a coil identified by a circle, or you might see it identified, I've seen it identified as a zigzag symbol with a circle, and that might simulate a coil. There's a number of different ways they'll do that, and typically we look at the symbols for that. And of course, the contacts, this one is showing me a set of contacts that is, in this particular case, is identified as, let's say, normally closed in this manner. Now, electrically, what it looks like is, and of course in this particular box or relay, they're identifying the power coming into terminal number 1, and so the coil terminals are 1 to 2, and of course they have a jumper that's going between 1 and 3, and that in some situations you might be adding it, in others you may not have it. But of course, when there is a jumper here, then you certainly don't need any additional power going into that relay as identified by that symbol here. So electrically, what does it look like? Very simple. So in this particular relay, they're simply identifying terminals 1, 3, 2, and 4, which represent the terminals that are identified on the relay. They would need to be. And then electrically, this is identifying the magnetism that is developed by the coil of a relay, so there has to be continuity. And then, of course, the action that should occur, whether it's moving up or down, is going to be determined based on, that's what this is doing, the set of contacts. So what you're seeing there is obviously what has to be seen there. Very basic type things, but those are expectations that if you're going to be a troubleshooter, you have to have some understanding or some concept of that in order to know what's supposed to happen. If I energize this relay, should it do something? So, but absolutely. All right, so a little bit further to dig into this. So we have a single pole double throw relay that's identified in the structure, and the single pole relay is going to really be, let's call it, identified in the poles as I have one, let's call it one power supply to some extent, or one feed. And in this particular case here, we are looking at, for example, I might say I'm going to use maybe 120 volts here. I'm going to go into this particular device, and I'm going to, so this one, we're going to call that, let's call it a common terminal to both the normally open and the normally closed set of contacts, electrically speaking. So this 3 would be common to both 4 and 5 terminals. Now, the throws would be, this one is a double throw. So we have within this relay structure, we have both a normally closed and a normally open contact that's identified here. So this is normally closed. This one here happens to be the normally open set of contacts in there. And then, of course, the coil is identified on terminals 1 and 2 in that case. So electrically, what does it mean for me if I'm the technician and I'm trying to troubleshoot this relay? I think to some extent what it means is that I would expect, if I were checking a relay by resistance, I would expect if I go between terminals 3 and terminals 5, I would fully expect to have continuity when the coil is not energized. So I would expect to have 0 ohms through that. And of course, 3 to 4, I would expect to have no continuity between those two. And of course, that would be an infinite amount of resistance that I would be getting, which should not allow any current to flow through that device. A double pole, double throw relay structure. So now, if you look at these two, comparing the previous one to this particular relay, one of the things I think you're going to recognize is we basically have, let's call it pole number 1. And in this case, this would be, let's call it pole 2. And of course, pole number 1 item is the terminal 3 would be identified as the common terminal of that set of contacts, just like the single pole one. But now we have a completely separate relay that is part of this common relay. So this one relay coil is supposed to provide action to both of those poles. So in other words, when I'm energizing terminal 1 and 2 to in an application, whatever that coil voltage happens to be, I would fully expect whatever happens between terminals 3 to 4, if I energize relay 1, I would expect the R1-1 to close. I would expect R1-2 to open up. And I would expect at the same time, I would fully expect R1-3 to close and R1-4 would obviously open up. And of course, there would be no power on there that would be sent directly to terminal, let's call it to terminal 8 in that case, because it would be an open set. So assuming that I took 120 volts here, I would expect the current to kind of flow through the relay when I energize that relay and send that on to terminal 4. And if I also have 120 volts here, I would expect this to go from 6 all the way through to terminal 7. And then there would not be any power, or I hate to use the word dead terminals, but they're terminals that are not going to carry any current flow, which is going to be terminal 8 and terminal, not 4, but terminal 5. And those are, the thing to be careful with, I guess, to some extent, is to understand what's supposed to happen with relays and coils and contacts, and to at least have some understanding that there potentially could be within a diagram, you could actually have power on terminals 5 and 8, even though that you are not providing any work. And it could be voltages that are being backfed from other devices. It could be another motor lead, as an example. So it's just something to be aware of. Even though that the circuit might be open, it still potentially could have some power on that. So again, the importance of this is to identify, what are the mechanisms that are supposed to happen in this circuit. All right, so let's talk a little bit about some of the time delay relays. And I think time delay relays, really with any type of time delay relays, is to provide some sort of a delay in doing something, whether it's energizing a circuit or energizing a relay or to de-energize something, depending on how it's being used. So it has some sort of a delay as part of that. So in this particular diagram, for example, they're showing basically, let's call it a multi-stage application with 4 compressor motors that would be attempting to start. Now, logically, it would make sense that if there would be a single demand or a major demand where, like, we want all the cooling we could possibly get, and somebody goes and enables cooling, what you wouldn't want to do in a normal job is you wouldn't want to have it where every single compressor starts at the same time. One of the problems that can create is a huge amount of inrush current that might be too taxing on the power supply of a system, and that could create some problems. So in this particular diagram or application, that's kind of one of the things that would go on in here. So if I were to look at the circuitry and to prevent any type of overcurrent problems with this thing, and I were to look at that, so for example, if I have stage 1 calling, and I would expect the high pressure cutout, go through the high pressure cutout, the low pressure cutout, and energize the number 1 compressor contactor coil. Now simultaneously, I'm going to be energizing through the high pressure cutout and low pressure cutout and energizing the time delay relay. Now the time delay relay coil will now, we're going to energize that. It's going to then go on the back side or the common side of the contactor, that number 2, and obviously as well as that as the other delay coil. So those are set up in there. Now what we're going to do is we're going to wait for a certain amount of time. So in other words, whatever that time happens to be, and maybe that time happens to be 30 seconds, maybe that time happens to be 5 minutes. It really depends on how they want the system to be structured. If the only intent is to minimize an inrush, you could put easily a 10-second or a 30-second delay to prevent any type of problem there, and it would be because a compressor should start really within a few seconds for sure and be up to speed. So that's kind of one operation. So at that point, after the delay, so let's put a D in for delay, then at that point we would close that after the time delay, and then essentially that would go and energize the compressor contactor as well, and then it would also energize an additional time delay at the same time. So there is no way that they would allow anything to occur at that point. So in other words, stage number 1, or this stage 1 would go on, stage 2 would go on for compressor 2, and compressor 3 would be waiting after the delay. So in other words, the timing of this delay would start after this one, after this second, or let's call it the first time delay relay is actually closed. So those are delays. So they're not like a normal relay where I energize it, I expect an action right away. These are ones where there's a delay in there, not for obvious reasons. That is its purpose. And then of course, further, need for cooling, close those circuits. We go through the high pressure cutout, low pressure cutout, and then we go through these contacts. Now, if the delay is not an issue, and let's say the first stage has been running and the second stage has been running, they're pretty much this particular set of contacts would close, and the second that the additional, let's call it second stage thermostat would kick on, that would close this set, and it would actually energize the next compressor contactor, number 3. And then, of course, additionally, it would energize the time delay relay number 3. Now, an alternative way to this would be that you would just have the time delay relay for each of the stages would energize the respective time delay. Now, in this particular diagram, the manufacturer of this particular diagram just decided that they were going to start the delay based on the previous stage of what would be going on there. It's just the way they chose to do this. So nothing right or wrong or anything. And then, of course, if there's a continual energization that's needed or some cooling additionally, they'll flow right through here, go through the contacts. After an appropriate delay is set up in here, that would close, and then it would allow this. So you're not going to get all of these compressors to operate and start up at the same exact time, which is what we want to do, and that's one of the reasons for the delay. So, and there's a number of different applications that we would do with that. Really, when you think about time delays in furnaces, we use it all the time. We give a furnace time to warm up the heat exchanger prior to energizing the fan, if it's let's say a residential furnace. If it's we can do it on rooftops as well. So, and primarily it's so we don't blow a bunch of cold air around. So it just kind of makes sense to do that. So lockout relays. Now lockout relays were an interesting one. We had done some activities with lockout relays and at least talked a little bit about these. And they're a special type of a relay, what we call an impedance relay. Some people call it a reset relay. Some people call it a high impedance relay. But there's a kind of a, let's call it a method to the madness. And what they're doing in these lockout relays is what they're going to do is they're going to kind of, let's call it chew up all the voltage or all the voltage. They're going to chew up all the potential energy because of a high impedance relay that would allow this circuit to operate. So in other words, what they're going to do now is they're saying that in this particular diagram, if we follow through this one, we're going to have an application where we have a control relay. Let me see if I can get a highlighter on instead. Yeah, there we go. And what we're going to do is we're going to energize this control. Something in the system would have to say, hey, we want cooling. So in other words, whoops. So we would say, hey, we want the control relay to energize. We need cooling. That would be an example here. So something has to happen, or maybe we want the fan to run, whatever might be going on. But in this case, based on what I'm seeing here, it's most likely going to be something in that order. It would be, we want cooling to operate. So in this particular case, that would allow the current to flow through, and it would actually allow it would go through all the compressor overloads. It would also go through the high pressure cutout, go through the low pressure cutout. Now, it would go through those. It would go through this normally closed set of contacts, which is part of an impedance relay, and it would energize the compressor contactor, is the way that would operate. Everything is all happy. Now, you might be wondering, well, why did this little lockout relay why didn't that get energized? And that's a good question. Why didn't that get energized? And a little bit of this is, to some extent, it's a, let's call it a path of least resistance. So what's happening here is even though you have, you really don't have any potential difference across the relay is what's going on here. So what's happening is if we measure our energy, if we were to measure our voltage from this point to this point, we really don't have any potential difference because all of these are going to be closed. And because all of those are closed, you really have zero, let's call it zero voltage difference is what I'm going to say in here. There's no potential energy difference. So there's no reason for the relay to be energized at that point. There's no work. So if I check my voltage, because the resistance from this point to this point, we would hope would be 0 ohms, electrically speaking. Because the difference between that point, that change in those two in the resistance, we know that relay will not energize. Now, the coil this compressor contactor will of course energize, but we want it to do that. So where lockout relays play a role is what they're going to do is this. So let me go ahead and get rid of some of this. And where the lockout relay happens and occurs is they're going to provide some action based on something that's got to happen here. So let's go ahead and try this. So we're going to take our power, we're going to go through our control relay, we're going to go through, and let's say go through a compressor overloads and the high pressure cutout, low pressure cutout. Now, watch what happens here. So this is a properly operating system where everybody's happy. But now, what goes on if all of a sudden the belt breaks on the fan, and or the fan motor fails, or the contactor fails for that, And let's say the low pressure control opens up. So we're going to open that control. Now what that should do for me is that should actually then stop the power from at this point. Now, at this point now, if I look back on this and I say, okay, now because this is open, what's going on is I have an actual potential difference in voltage across that relay. So if this happens to be, let's say it's a 24 volt relay as an example, what would happen now is I'd have voltage available there, and I would have roughly approximately 24 volts of potential difference across there. Now what you have to understand now is that electrically speaking, the energy, the voltage here is going to allow us to send power through the relay. And of course, one of the rules or the laws of Ohm's law says electricity will take the path of least resistance. So electrically speaking, this lockout relay coil, plus the resistance of this coil is, let's call it one and the same. They're basically going to be in series with one another. And as we know, the voltage, let's call it the voltage drop, or the voltage drop in a series circuit so in series is going to be proportional. Now, so what this means now, if the voltage drop in a series circuit is proportional, that pretty much would tell me that if I have a total potential difference between your entire power supply, let's just say if that happens to be 24 volts, and let's say this one here happens to be, let's say this one happens to be, let's call it 100 ohms, and this one here happens to be 10 ohms, or let's say this one here, I'll change this to make it simpler here. Whoops. So if this 24 volt system here happens to be, let's call it 90 ohms. So total we have 100 ohms. So here's the kicker. So the 90 ohms is going to get 90% of the 24 volts. And this coil will only get 10%, which would be about 2.4 volts of drop across this coil. However, that's not enough to pull this contactor in, but it's enough to pull the cooling lockout relay in. When that happens, then this will open up, that set of contacts. And so then this normally closed set of contacts is actually going to open up in that case. So that's what's got to happen. What will happen now is that will not be allowed to function again until the circuit is broken, or you interrupt power, or you reset the control. So if this were to be a manual reset control, I would have to correct that problem or reset it to allow that to happen. So the whole idea of this is they don't want things to be, let's call it, operating out of sequence or allowed to operate to some extent. So you have to be able to interrupt power, fix the problem without any issues. So that's kind of one of the things. So but that's, like I said, they've been used for a long time in a number of manners. Many of the manufacturers, they might even have these built into some of their logic controls on there. But it's a great little strategy of how they do this. But that's, electrically speaking, that's how they function. All right. So contactors and motor starters. And of course, then one of the things that we had discussed was, well, what's the difference between a contactor and what's the difference between a motor starter, or what's the difference between a contactor and a relay? Well, when we talked relays, relays typically are going to be limited in that, let's call it that 15 amp range and at most, as a general rule. Usually you start looking at contactors when you start exceeding 15 amps. So our larger loads have to carry those things. Our larger motors, our larger loads that are pulling more current would be a contactor is a very good application to use. Now, a motor starter, on the other hand, is, let's call it, it's essentially a contactor with some sort of protection, some overload protection that would allow, in the event that we would pull an excessive amount of current, that through a circuit, through one of these legs that would be going through the contactor, the overload would allow that circuit to open up and stop the contactor at that point, is what would have to happen. So those are, some of the motors will have this, some of the motors don't really need it. It just depends on the application on there. But a lot of our commercial applications we do indeed need those to function or to happen. Now, you might also notice in this particular application, this particular magnetic starter that's shown in here, what it's showing here is it's showing a reset button. So after let's say one of these circuits, these overloads in here, kind of trip the circuit or open up the set of contacts that are part of the overload relay circuitry, that once those, if you open one of them up, it opens up the whole circuit, because those three are going to be in series. When you, once that, let's say that problem is corrected, a person can, or checked out or corrected or verified that the issue is resolved, a person can reset by pushing in this little red button. In this particular case here, they can push that reset button in there, and then that will reset the overloads and allow them to kind of operate, the starter operate as what's needed on there. So, and that's typically what would indeed happen. Most of your air handling units and things like that, they typically would indeed have some sort of a motor starter. All right, so there are a couple of ways to test some of these. Let's talk about checking, switching and contactors and relays and some of the circuitry. So typically there's two trains of thought. One of them is if I need to test a circuit that does not have power and is isolated, checking resistance is sufficient, it's adequate. So this one here clearly identifies that we have on a system with, let's say, 0 ohms, that would identify it a normally closed or a closed set of contacts. And if I have an infinite amount of resistance, that's an extremely high level of resistance, that would identify an open set of contacts. Now, usually that's what they should read. When you expect them to be closed, you would expect 0 ohms. When you expect them to be open, you would expect an infinite, a very high amount of resistance. It's either all or nothing. When you are testing those and you start to pick up resistance, that's telling you those sets of contacts are really not functioning correctly, and you got to kind of fix that. Usually that means replacing the relay. So that's something to remember. Now, in voltage checks, now let's take a look at this. So a closed set of contacts. Now this kind of ties in with what we had talked about earlier in the control circuitry, is in this case we're showing 0 volts on a closed set of contacts. So if I expect a set of contacts and I set my voltmeter to volts, I would expect when I go across a set of contacts that I would get 0 volts if it's closed, if I'm expecting to be closed. If it's an open set, I will get whatever the potential voltage would be. So if you have 240 volts running through a set of contacts, you would expect 240 volts. Where a person has to be careful on those types of applications is you have to be very careful that the rest of the circuit is actually closed. So in other words, if I were checking this particular set of contacts over here, yes, I would expect 240 volts. But what if downstream there's an additional, let's say, relay, or there's an additional load or a motor that has a broken circuit? So let's say they have a winding that's out. and you don't have a complete path. Even though you've got voltage brought to this device, it will still not show 240 volts if there are multiple opens within the circuit. And that's the part that a person has to be very careful with on testing those. But in a typical system, I would say yes. That is that would be typical what we would normally expect to see. But a person has to be somewhat careful on testing these and testing going across contacts without that understanding. All right, so let's talk about some switches and pressure switches and in these particular cases. So for example, in this particular application here with pressure switches, I've got fixed pressure switches. They would be typically used for some sort of safety as hey, I don't want, it's a high pressure control, or it's a low pressure control, or a loss of refrigerant in a system. That would be an example. There are safety controls that are adjustable. The ones that are identified here, that's seen this way, these are fixed. They are not going to allow any adjustability on those. So when you order those, you have to order them with the correct pressure that you want it to function as. So pretty straightforward. The one that's identified right here, that particular control has a resettable button on it. So that would be an example of let's say a high pressure control or a low pressure control that would be a loss of charge type control. They would, if the system were to fail, you'd have to push that little red button into the control to reset the safety, and then it would allow it to function again. So that's one example. This particular control here is an adjustable control, and there's usually going to be some sort of a setting up and down on the top of this one that allows the adjustability, whether it's higher or lower, and a person has to look at those. They're not all the same. There are, whether you're setting up a Honeywell or a Penn or a Ranco control or whatever the pressure switch controls might be, a Danfoss, you have to know and look at what you're looking at to make those adjustments. There's another system here that's also what they call, let's call it a differential pressure switch. So for example, where a person would use something like that would be in the event of, let's say you're checking, let's say oil pressure inside of a compressor. So some of the compressors that have an actual pump, they would have the ability to have a safety control that would look specifically at the pressure on one side, the low pressure side here, versus the oil side and the other side. And they would have to be mechanically piped into that system. And then of course that usually those are adjustable, but there are some that are not. So there's a lot of different types in there, and those are typically to protect the compressors against failure and things like that. So, but we have a number of different applications. So differential could be a good example of differential would be like a furnace pressure switch as an example. So if you had a pressure switch that would open up, that would tell you, hey, there's something wrong with this as a potential case. So, all right. So the next one we'll look at here in item 1.2.2 is a freestat. And the freestat allows me to provide some sort of a low temperature protection on a chiller. So for example, on a normal chiller, I might not want to go down below a certain temp. So if, on a typical application, I might say I want 54 degrees Fahrenheit coming back for chill water into on the return side. But on the outlet side, I may expect to see, let's say, 45 degrees or 44 degrees as an example, something like that as an example. So what would happen now is if for some reason, let's say that there's a strainer in the system, and of course if the pump, that all of a sudden the pump decides that it's not moving water, what we would have, there would be other safeties that likely would try to do that, but what if those safeties are not functioning? So what we would have is we would have a freeze thermostat that would look at the water temperature that would be usually very, very close to this particular chiller barrel. And so we may look at the outlet temp on there. And what we want to do is prevent anything from freezing up in there. If that water temperature gets down below a certain level, we may say, hey, we need to stop this unit from running. Typically, on a chiller, we might say, let's not let it go down below 36 degrees to give us a little bit of flexibility, a little bit of safety margin is normally how that would work. So freestats, can be higher, they can be lower. A good example is if you happen to have, let's say, a geothermal heat pump, and maybe you're running a glycol in that circuit. You'd still want to make sure that you don't freeze up the chiller barrel or you don't freeze up the coaxial coil. So what you would be wanting to do is to make sure that you are looking at the controls to determine what the freestat protection would be. So for example, if you're running water, you know that the water would freeze at 32, so you would want to make sure that you are not getting close to that. So you might cut it out at 35, 36 degrees. If you're running glycol, which maybe it has freeze protection down to 10 degrees or 15 degrees, you may be normally running a temp on that glycol loop that could be as low as 20 degrees or 25 degrees. That being said, you would have to make sure that you have the freeze thermostat that's adjusted for what you're trying to protect or what you're trying to save. So again, not difficult, but that's normally a very important device. Typically, freeze thermostats and freeze safeties, they really need to be looked at or checked over and verified on a regular basis to make sure that they are actually functioning correctly, or you can really have some damage that goes onto a system. So that's kind of the one way. All right. So the next circuit that we're going to take a look at in this application is going to be a fan control, furnace fan control, limit control. And in this particular diagram, I'm going to switch to a highlighter. And in this particular diagram, what we have is, as we're running our power into our device, so we'll have, let's say, in this example, we've got power running to here, then to here, through the limit control, and that is, let's call it, that's feeding the transformer in this case. And we also have power going down to this particular set of relay contacts. So now, we're ready to do some work on this. And of course, the limit control is designed to take the power away from the transformer should there be some sort of a failure of high limit usually, or high temperature of some sort. And this would be one simple way to do it. Now, of course, on a normal system, it's functioning correctly. We would expect that our low voltage side would drop down to 24 volts maybe. We'd go through the thermostat. Assuming there is a demand, we might energize some sort of a pilot mechanism, main gas valve, and so on and so forth. So this would be closed typically because of the pilot safety that we deal with. And then, of course, the main gas valve would be energized upon a thermostat demand, that this would be closed. Now, I'm assuming at this point we would expect that we're heating the application. As we're heating that application, you would expect that everything is working correctly. But what in the event if this set of contacts were defective down by the fan control? And if that were to be defective, well then of course that fan motor wouldn't run. Chances are you would say, you know what, that high limit better open up. And when it opens up, most of us would fully expect that we would then lose power directly to the transformer, which of course would shut off the main gas valve, take away power. Everything down here would lose power. All of this would lose their power. On a normal properly operating, and it would actually keep that way, it would stay off until that limit control is going to reset itself based on temperature in this case. Now, in a properly operating system, what we would expect to have happen is we would expect after a certain amount of time, after you energize, you have a heating demand, the safety is closed, we have the main gas valve energized, we're expecting heat to be going on, and we're heating the heat exchanger. And we would expect that fan control to be doing its job. And after a certain amount of time where you would, let's say, allow it to energize or allow it to close a set of, or warm up, we would allow that set of contacts to close, and that would allow voltage directly to have that circuit be completed. So we would allow the fan motor to be functioning appropriately, and everything would be working correctly. And that's what you would expect. So we have all those limits. Now, most of the time, a lot of these limits and the fan controls typically are going to be built into a circuit board nowadays, based on some sort of timing as opposed to, let's call it a thermal device. The limit controls would not be. However, they would be wired directly into a circuit board, usually in series with the gas valve. And many of these are going to be on the low voltage side, but there are some that are on the high. So this limit control really could be here, or a person could even put it in this circuit over here if they wanted to. So there's a number of ways that we could set that up. I've seen them in a number of places. So that's normally how you would set that up. This one here identifies a combination fan and limit control. And one of the things that you have to take a look at is many of our industry, what's gone on in our industry is we've primarily we've gone to timing of fan controls, and whereas this, the fan and control, or the fan control would be done that way. But there are some equipment that is still used today that use a combination fan and limit control, and they may be using that to provide some sort of a function electrically. So what would happen though on the old traditional, let's call it combination fan and limit control, what they would do is they would have a jumper that would allow the power to go between, let's call it the fan side and the limit side. And so the main thing a person has to recognize is that the reason why one would do that is if you are having a transformer, the fan is typically on the high voltage side. If the transformer is on the high voltage side, you might probably want that jumper intact in that combination fan and limit control. However, if the transformer is set up for low voltage, then you absolutely have to take that control, you'd have to get that out of that circuit. So in other words, that little device that's there, one would have to get rid of that. So you'd cut that jumper, you'd remove the jumper, you'd break the jumper. That would go between that side. It really depends on the control. So if you're using a Honeywell control, you might be breaking a tab. If you're using a White Rogers control, you might be not breaking a tab, but you might be taking an actual jumper out, or metal jumper out. So you just have to know what it is that you're kind of dealing with. But that's the big thing to remember, is that you have high voltage sides and low voltage sides, and you have to recognize what you're dealing with, so you know what you have to do on those. So the one that's on the top, so this is the lower one, and this one would have the high voltage transformer. It would have that transformer on the high voltage side, and the one that's on top up here, you'll probably notice, is that the jumper is taken out. So that allows me to have the 24 volt circuit to be completely isolated. Even though it's in the same control, there are two completely separate controls that are built into the same unit with two sets of contacts. So one of them opens on a rise in temp, which would be the limit, and the other one opens on a fall in temp, which would be, of course, it would close on a rise in temp, and that would be the fan side. So if you think about the operation of it, that would be typically how that would work. All right. So that will conclude that first section, I will go through these review questions really quick. Talks about, a technician measures 230 volts across a set of normally open contacts and the relay's coil is energized. What would this indicate? Well, if you think about, what would a normally closed set of contacts provide us if it's a normally open set of contacts and you have that relay energized, you would expect those to be closed. So if you're getting 230 volts, you'd almost think that those contacts are not closing, which would be typically out. So it's saying the contacts are still open, the relay is defective, you'd have to change the relay out. The second question talks about a furnace limit control is wired into a gas furnace. And how would this be wired? So a furnace limit control would be wired into a gas furnace in. So your choices are parallel with the fan switch. It would be in series with the fan switch. It would be in series with the control circuit or in parallel with the primary transformer. So typically limits or those types of safeties, I think you would want those wired in series. But it would not be wired in series with the fan switch. I think it would have to be wired in series with something related to the control circuit in here. And of course that would be maybe in series with the thermostat or the gas valve or something like that. All right, so that will conclude section 1. And I will do a separate video for the section 2.